All right, section 11.6 is about gradients and directional derivatives. And we're going to start out just learning what a gradient is and how to calculate it. So the gradient of a function f of x, y is going to be denoted by grad f, this kind of upside down triangle. And it's going to be a vector. And inside that vector, we're going to put all the partial derivatives. So df dx and df dy. And then if you have a function of 3 variables, I'll denote it g to be like different than above. The gradient follows the same rule. You denote it by grad letter, and you just fill that gradient up with partial derivatives. So just for the first one, we had, that like z equals f of x, y we've been thinking about most of the time. So there were only 2 derivatives, but I just want you to know that if you have a function of 3 variables, you just have a 3-component gradient. And then something that's important to note about gradients is that they're vector valued functions. So just like when you take a derivative of something like, let's do, if you had f equals x squared, then the derivative is still a function of x. So this whole gradient is still going to be a function of the original variables. And if you just wanted to note, actually, I'm going to get rid of that name for it. But if you want to denote evaluating the gradient at a point, you're just going to do it the same way you denote a function. So you can do like grad f of x0, y0. And then you still fill in your derivatives, but now you evaluate them at each point. Like that. If that notation means something to you, good, remember it, but I'm actually going to erase it because a lot of people find that notation kind of intimidating, and I don't want you to think this is a complicated thing, and also because I won't have room to write the G one. So when you write this, it's saying evaluate the gradient of f, which is this special thing, plugging in the points x0, y0. We're not talking about like multiplication of the gradient by a point or a vector or something. And we're just going to practice calculating some gradients real quick. So for the first example, we're given f equal to x squared y plus y cubed. And we're just going to find the gradient. And so kind of a way to make sure you don't like get lost at any point is to just calculate your partial derivatives and then put them in the vector. So my partial derivative with respect to x here is 2xy plus 0. And my partial derivative with respect to y is going to be x squared plus 3y squared. So then my gradient vector, I just fill up with these 2 components, 2xy x squared plus 3y squared. I could also write it in like I hat, j hat notation. That's still fine whenever you want to use it. I like the angle brackets when I'm going to have lots of pluses and minuses because I think the parentheses start to get a little overwhelming, but you know, that's your choice. And then if somebody had told me to evaluate the gradient at the point, I don't know, 1, 2, then I could have just gone ahead and said, there's my grad f, and I want to evaluate it at a point, so I'm going to go like that, I guess. I want the points 1, 2, where this is my x value, that's my y value. And so everywhere I see x or y, I'm just going to plug in these numbers. So x becomes 1, y becomes 2, x becomes 1, y becomes 2. So that's 2 times 2 is 4 in the first component, and then 1 plus, 4 times 3 is 12, plus 1 is 13. So that's the gradient at a point. It's a number, but still a vector. If somebody tells you to find a gradient and you end up with not a vector, something went wrong. And this up here was my gradient in general. So a function and a vector. Let's see. And then I'm just flipping through your textbook for the problems in the book to find one that uses a function of 3 variables. So here we go. They gave us g of x, y, z equal to x, y, z squared. And we're going to find grad g. And so again, I'm just going to take all my partial derivatives. I'm doing it kind of like slowly and deliberately here to model how you could do it if you're ever worried about making mistakes, but soon I'll jump to the point where we just put our partial derivatives in the gradient. So with respect to x is yz squared. With respect to y is xz squared. And with respect to z is 2xyz. And so my gradient is going to be yz squared in the x component, xz squared in the y component, and 2xyz in the z component. And I could evaluate this at a point as well. So let's say I wanted grad g of 1, 2, I guess 3. So 2 times 9 would give me 18. 1 times 9 would give me 9. And 2 times 1 is 2. Times 2 is 4. Times 3 is 12. So it works the same way as before. I'm not going to box those because they're too close together. One thing that I want you to note real quick is that I feel like some people have gotten a little bit confused sometimes when we have vector value functions where there's like x's in the y component and y's in the x component. So that's totally fine. We can see here that there's like a y value in the x component, and it takes on different values depending on what point you're at. So these gradients are going to be little vectors that point in different directions at every point in space. And that's what they're supposed to do. So if you get an answer like this where there's variables in every component and they don't match, like this is the x coordinate, so you think it should only depend on x, that's not like a connection that is necessary. So this is really the sort of thing that they'll look like.